This conference will now be recorded.
Good afternoon, one and all. This is Rajesh. In our subject Embedded System Design, we will see the design approaches and development languages for our embedded firmware. So we have seen our embedded firmware, the introduction part, embedded firmware, the reset circuit, brownout protection circuit, the oscillator circuit, real-time clock, and the watchdog timer. So these are some other ICs. They are available part of onboard communication interface between your hardware core and sensors and actuators connected to your input output ports and the memory. So your embedded system is consisting of an hardware and software. This hardware, along with this hardware, we are having some other small peripheral ICs connected on the onboard, doing a task like generating a reset signal, controlling the various portions of your IC, generating a clock, monitoring the time, and how your firmware is executing. So such all is done by these components. In this video, we are going to discuss about embedded firmware design approaches and embedded firmware development languages. So as we have seen, our textbook is Introduction to Embedded System by Shibu KV. So coming to our objective, the objective of this video is you have to understand what are the design approaches and development languages for designing an embedded firmware. So embedded system is a unique system consisting of an hardware and software. The software portion is stored in the memory. The hardware processor is going to read the contents of the memory, which is called a control algorithm, which tells how an embedded system must behave, for which it interacts with the external world through sensors and actuators. So these are examples of embedded system: household appliances, telecommunication, medical equipment, industrial control, consumer products. So once again, we'll define embedded system. It is an electromechanical system designed to perform a specific function, and it is a combination of hardware and software. And the software other name is firmware. And in this firmware topic only, we have to see how a control algorithm is written, which tells how your embedded system must behave. And this hardware software interaction is controlled by an operating system. For medium and large scale embedded systems, we require this real-time operating system for scheduling the tasks as well as assigning the priority. So once you switch on the power, this embedded system will automatically run without human intervention, and it also interacts with the environment, external world. So it is reactive system. Then these are some examples. And your embedded system can be thought of as a microprocessor, microcontroller based system, which is designed to perform a specific task. So for a specific task, your embedded system is designed. And these embedded systems are unique systems, and the control algorithm is differ among them, will differ among them. So the control algorithm designed for your air conditioned system or the control algorithm designed for a washing system is different. So these embedded systems can be viewed as a reactive systems. They interact with external world, they react to the events or the changes in the environment variable or changes in the required variable, and for which we use common user interface input devices like keyboards, push buttons, and switches. And the memory of the system is responsible for holding the code. So the memory of the system is responsible for holding the code. The control algorithm is stored in the memory, and it is the code due to which your embedded system will operate. So you can see under elements of embedded system, this is the system core connected to the input ports to which we have placed sensors, and this system core is connected to the output ports to which you have placed actuators, and this system core is connected to so many other ICs, and this is connected to the memory in which we have stored the control algorithm. So this processor is going to control total embedded system. So embedded firmware refers to the software portion of your design, the control algorithm available in the memory, which can be written in two methods. One is two languages. One is embedded C++ in an IDE environment, or assembly language. And as discussed in from the previous slides, uh, writing code in a high level language is more easier compared to assembly language, because for assembly language you need to understand the instruction set of the specific processor, whereas high level language you need to understand only the concepts available in the language. So we have seen other system components such as reset circuit, brownout protection circuit, oscillator circuit, real-time clock, watchdog timer, and other passive components. So our topic is embedded firmware design approach and development languages. So for which again we'll introduce what is an embedded firmware. Embedded firmware is nothing but the control algorithm or program instructions and the configuration settings where a developer dumps into the code for to make the embedded system behave as required. And it is unavoidable part of your embedded system. It is developed in mostly in embedded C++ or an assembly language. Embedded firmware design and development. The embedded firmware is responsible for controlling the various peripherals of the embedded hardware. So you can analyze the embedded firmware is responsible for controlling the various peripherals of the embedded hardware and generating response in accordance with the functional requirements of the product. So the embedded firmware is the master brain of the embedded system. The embedded firmware is the master brain of the embedded system. It imparts intelligence to an embedded system. So your firmware is the main portion which tells how your embedded system must behave, and it is a one-time process. Once it is written, it can happen at any stage. It is a one-time process and it can happen at any stage. The product starts functioning properly once the intelligence imported to it is enabled, and the product will continue serving the assigned task till hardware breakdown occurs or a corruption in the software occurs. So your software must be corrupted or any hardware must be interrupted by a power supply or any other mode. Till then your embedded system will operate as required. In case of a hardware breakdown, if there is a hardware breakdown, what happens? The damaged component must be replaced and the firmware corruptions should be reloaded to bring. So if there is a firmware correction, you have to send it to the manufacturer and the firmware is rewritten and the product is used for normal functioning. Whereas if hardware breakdown occurs, maybe some component will be replaced. The embedded firmware is usually stored in a ROM, read-only memory. See, the memory is of two types, ROM and RAM. Random access memory stores the data which is generated in between and the executions of the control algorithm, whereas the control algorithm itself is the program which tells how an embedded system must behave, and this control algorithm is stored in a ROM called read-only memory. So how to design this embedded firmware? Designing an embedded firmware requires understanding the various components of your hardware, how to interface, memory map details, IO port details, how many registers are there, and what language you are using. So this all is required before you start writing your program, and for which you need to know the development languages. So for which you can use the modeling techniques. So there are two approaches. Embedded firmware design approach is that there is a two approach, whether you use high level language or use an assembly language. The first approach is called a super loop based approach, and the second approach is called embedded operating system based approach. So the decision on which approach is adopted is purely dependent on complexity and system requirements. So based upon the complexity and system requirements, you have to select the approach. So first one, if you are seeing the super loop based approach, the super loop based firmware development approach is suitable for applications that are not time critical. So we are just writing your high level language on an IDE or an assembly language by using a super loop based approach where not time critical, such as electronic toys, washing machine, they are not time critical. If there is a minute delay, we can accept such systems where response time is not important, for which you can use same languages, either you use the embedded C, C++ or assembly language. You have to go for this approach. So what is there in this approach? You write the code task by task, which task is executed and after which task must be run. So like task by task they are written. First you are going to configure all the common parameters and perform initialization of all the registers and memory. Then you start writing the first task, then execute it. After that, it means you have written the task and how it is executed. Execute the second task. So like that all the tasks are written, and based upon any interrupt, again jump back to the task it is provided. So your embedded system will be executed based upon these tasks. So if you see the C program, super loop approach means first main, all configuration and initializations are done, then using a while loop we are executing first task, next second task, so on in tasks. So for because we are using a C language and we are writing all the control algorithm in terms of different tasks. So each operation, like printing to a monitor or taking input from the keyboard, all the different tasks. So they are done written as a loops in a while loop. Then it does not require operating system for task scheduling, and they are free from operating system overload. So what is the enhancement? Enhancement means you can combine super loop based technique with interrupts. You can add some interrupts and execute the tasks which require real-time attention as interrupt service routers. If you go to the second method is a embedded firmware design approach where we are using a real-time OS operating system, embedded OS, a real-time operating system is used, which is different from a general purpose operating system. So in what way we'll see, this embedded OS is responsible for scheduling the execution of user tasks. So in embedded OS, which is called real-time OS, we are having something called the main portion of your OS called kernel. This kernel is going to do task scheduling and priority, which is not available in general purpose OS. So Microsoft Windows XP is an example for general purpose OS for embedded devices, and point of scale terminals, gaming stations, tablet PCs are examples of embedded devices running on embedded GPU OS. So Windows CE, Windows Mobile, QNX, VxWorks, ThreadX, Micro COS2, embedded Linux, these are examples of real-time OS employed in embedded product development. So your mobile phones, PDAs, and flight control systems are examples of embedded devices that run on RTOS. So we are having some more devices which are so at this point to understand, there are two OS. First one is super loop approach. Second one is embedded OS based approach. In embedded OS, again you can use a real-time OS or general purpose OS. In real-time OS, you can go for task scheduling and priority. And what are the different operating systems available are Windows CE, Windows Mobile, QNX, VxWorks, ThreadX, Micro COS, C/OS2, Embedded Linux, and Symbian. These are examples of RTOS employed in embedded product development. So our next topic is, see, approaches of two types: super loop based approach and embedded OS based approach. Under embedded OS based approach, you can write same assembly language or high level language using either embedded OS based on real-time OS or general purpose OS. Coming to language, embedded firmware development language options are, you can use an assembly language which is consisting of or high level language. So it is a subset of C, C++, or you can mix all these languages. So first one is embedded firmware development languages, assembly language. So assembly language is human readable, and machine language is a processor understandable. Assembly language programming is the process of writing the processor specific machine. So based upon the target processor instruction set, this assembly language is written by using an format called label, opcode and operand and comments, and each instruction is read by the processor. Like your 8051 move a comma hash 30 will move the decimal value 30 to your 8051 accumulator register. So like that each of your instructions are written. And there is one more point. The assembly language is written like delay. This is the label. Move r0 comma 255. So they are loading your r0 with 255. Then after that in r1 register they have mentioned a delay. So once you decrement it, it becomes until it becomes 0, this loop gets executed. And the second language is assembly language, where your source code written in an assembly language will be converted to the machine code by your assembler. So this in this diagram, this is a source file 1, source file 2, source file 3. So there is a assembler which is converting it to an object file, and it is sent to your library. Along with your library files, it is hex file is generated. So your whatever the assembly code is written, that is converted to an hex file with the help of library files. So what is the advantages of going for this language is efficient code memory and data memory usage, high performance, low level hardware access. So if you go for high level languages, it is using the memory efficiently for code and data memory, high performance and low level hardware access, code reverse engineering. And what is the drawback is high development time and developer dependency. So and the third approach is we have to mix assembly language with high level language. So here mixing also takes place in 3 methods. Embedded firmware development language, in which we want to mix assembly language with high level language. First one is you can mix your assembly language with high level language, or you can mix high level language with assembly language, or it is inline assembly. The the passing of parameters and return values between high level and low level is a cross compiler. So generally high level languages have a compiler with to check the syntax. Low level languages like assembly language has a assembler. All assemblers and compilers will convert your code into a machine readable. But when you are writing a portion of code with assembly language and a portion with a high level language, you require cross compilers. The first method of writing the code is mixing assembly language with high level language like C. So we are mixing assembly language with high level language like C with the assembly language. And third one is inline assembly. What is this inline assembly is you want to insert target processor specific assembly instructions at any specific location of source code written in high level language. So inline assembly avoids the delays in calling an assembly rotate from a C code. So this is given example pragma move a comma hash 13 h pragma en same. So key C51 are the keywords in order to indicate this inline assembly. So with this I'll can conclude this, but I just will go through our third unit. Embedded firmware is telling about what is an embedded firmware, what are the other passive components available on the board, and how you develop your embedded firmware, the control algorithm which tells how your embedded system must behave. The control algorithm is developed in high level language such as embedded C or C++, or it is developed in embedded uh, it is developed in assembly language. First one is embedded C, C++. Second one is assembly language. These two can take is two approaches. One is super loop approach, where it is written as a set of tasks and there is no time critical and no priority. But when you go for embedded OS, we can go for a real-time OS where task priority and task scheduling is done compared to your general purpose OS. So with this, I'll stop my session.